talked and chatted, I think, enough to cover the things we needed to. Whoop. Share screen. Okay. Chemical reactions, here we are. So let me grab the chat so that I can see it. We'll have some poll questions and things today, so get ready for those. But let's get into chemical reactions. So I'm assuming that you have learned from last week's videos how to balance a chemical reaction, and then the 5 classifications that were introduced last week: combination, decomposition, single double displacement, and combustion reactions. So today we're going to actually learn about 3 more common types of chemical reactions. That's essentially all we're going to cover, and then we'll try to review some other content. So let's jump into this. Common types of chemical reactions. The first one we'll talk about is called a precipitation reaction. I'll abbreviate reaction. So you should be familiar with the word precipitation from like the very first week of class. We said a precipitate is a solid that is formed in a liquid, okay? So what happens with precipitation reactions is you mix things that are clear or translucent, and you get something that is a solid. And a solid dispensed in a liquid looks a lot like this. It looks kind of powdery. Sometimes they're colored, sometimes they're white, which is a color, but they can sometimes be hard to see, sometimes they're a lot more obvious. So this occurs when water-soluble reactants react to form one or more insoluble products. And the insoluble product is the precipitate. All right. Now, let's look at this reaction we have here. And in fact, that's what's being showed in the picture with the beakers and the hand. We have a solution of lead nitrate. That is this right here. Pb is lead. NO3 minus is a polyatomic, you should know, nitrate. So we have lead nitrate. And what does AQ mean? Anybody remember from last week in the videos? We talked about sometimes you abbreviate aqueous. People say it different ways. Okay, so this is an aqueous solution. That means you have water with these ions floating around. Okay, that's what makes a solution. So I'm going to assume that's, I don't know which beaker it is. Initially, we start out with 2 clear beakers. So that's one of the beakers there on the left. Then you also have an aqueous solution of Ki. What is Ki? That is potassium iodide, right? Dide meaning it's an anionic compound. So you have 2 aqueous solutions, and they're both clear starting out. And the moment you start to mix them together, you get this bright canary yellow type of precipitate. And what did we form? What is making that? Well, if we look at our product side, we have potassium nitrate. And notice right here, that is aqueous. So that is not our precipitate. That's not the bright yellow compound. But we have PbI2, and if you'll notice, the physical state of the matter is indicated as an S, and that means it's a solid. Okay, so that is what a precipitate is, a solid in a solution. So that is our precipitate, lead iodide. Okay, most things with lead are not soluble. So lead iodide is the precipitate, and here I want to make the point that indicating the physical state, those abbreviations after the formulas are crucial. How else, if we had none of those abbreviations, how else would we know that we have a precipitation reaction? So those are absolutely critical when you are writing a precipitation reaction, or when you're looking at one and you're trying to decide, is this a precipitation reaction or not? You look at the products. If you have one that's a solid, that's an indication that you formed a precipitate. That's a precipitation reaction, okay? So how do I know if I have a precipitation reaction? You look at the physical state abbreviations, and if you have a product that's a solid, you have a precipitation reaction, okay? I'm also going to introduce this next slide. It's a solubility rules. So even if I didn't have those abbreviations, okay, the AQ and the S or the L and the G indicating the physical state, if I have this table of solubility rules, I can look at my products and I could figure out if one of them would be solid or not, or if they're all aqueous. So solubility rules are guides. As we've studied the chemistry of different ions and compounds, we've learned to predict what things will be insoluble in an aqueous solution or not. Okay, so these are general solubility guidelines for, notice, ionic compounds. So we're not talking about covalent compounds here, we're talking about cations and anions. And in fact, if you look up at this reaction, both of these reactants are ionic compounds. And that's a pretty good indicator too that you're going to have a precipitation reaction is usually between two ionic compounds. Okay, so let's look at these solubility rules. If a compound has, I'm going to talk about the column on the left first, where it says soluble right here. If a compound has one of these ions, notice that they're either cations, so these four right up here are cations, and everything below that are anions. If a compound has these cations or these anions, it will be soluble in aqueous solution. So if you have a compound and the cation matches one of these top four, or the anion matches one of these bottom, I think it's 7, that compound will be soluble. Now, we're going to talk about, there's a couple exceptions, but for most of these, there's no exceptions. I'm going to draw a line here, a line in the sand. Right here, below acetate. I'm going to draw a line because everything above this red line, there's no exceptions. So if your compound contains one of these anions or cations above the red line, that compound is always soluble. It will never form a precipitate. Okay. However, the compound will also be soluble with these anions below the line, unless it is combined with these particular cations. Okay, so let's look at that. Let me go back to my original color here. So, for example, we have Ag plus as a cation. If Ag plus is combined with, I think it's these 3 anions right here, Cl, Br, or iodine, okay? Those match up with this. So for example, if I have the compound, I'm gonna zoom in, I gotta write the cation first. If I have the compound AgCl, normally, something with chloride as an anion is soluble. However, because it's combined with silver here, and silver is an exception, silver chloride would be a precipitate. It would form a solid. Okay, let's look at another example. We have barium. Sulfate, if a compound contains sulfate, it's usually soluble, but if barium is the cation, BaSO4, we got a +2 and a -2, so they're balanced with 1 each. If you have barium sulfate, that is going to form a precipitate. Okay, so pay attention. Silver, mercury 2, and then lead, lead +2. If these are the cations for the chloride, bromide, or iodide anions, those compounds will form a precipitate. And then if barium, mercury 2, or lead 2 are the cation for sulfate, those compounds will be solid. So let's check your understanding here. I want you to look at these compounds. I'm going to zoom out so that you can try to see the solubility rules, as well as these A, B, C, D, E compounds down here on the next slide. I'm gonna run my first poll. So the poll is these 5 compounds. We'll do one at a time. Actually, I think you have to answer all 5 before you can submit your response. All right, I'm gonna launch the poll. Okay, so I'm just asking you, is the following compound soluble or insoluble? Okay, which is the same question posed on the slide. Which are soluble in water? Aqueous solution, water, kind of, that's the same language here. So look at this first one. It is CdCO3. Cd is cadmium. It's the cation. And sorry, I could not use subscripts on these polls for Zoom. So the first, question number 1 corresponds to compound A. All right, let's actually walk through that first one together. Is it soluble or insoluble? And then you'll do B, C, D, and E. And you're looking at the solubility rules to help you make these determinations. Okay, so CD and CO3, basically you say, are these on my solubility rule chart anywhere? If I look up here, I don't see CD, that's the cation, and I don't see CO3, that's the anion. So because these are not soluble, this one will not be soluble in water, that will be insoluble. Okay, so apply that same thought process to the rest of the compounds, lead sulfate, mercury to chloride, sodium sulfide, and ammonium phosphate. So I'm gonna give you a second to think on those. We got about 50% of you have voted so far, so I'm going to give it another minute. And then we'll talk about these. Seeing some pretty even answers on some of these responses. About 7 more people. All right, we're 96% voted. Okay, I'm gonna call it. Speaking, oh, 100%, there we go. Speaking of voting, if you're not registered to vote, I think this is the last week to make sure you're registered. I learned that myself yesterday. Okay, let's look at these. So we said cadmium carbonate is going to be insoluble. So most of you voted insoluble, and that's the correct answer. All right, let's look at lead sulfate. Okay, so we said sulfate, which is right down here at the bottom, is going to be soluble. It's in the soluble column. So if a compound contains sulfate, it'll be soluble unless it has these cations. Well, it happens that here, Pb2+ is our cation. So lead sulfate is going to form a solid. All right, so it also would be insoluble. Now, 12 people, 40% voted that it would be soluble. Normally, sulfate, if it's in the compound, is soluble, but you have to consider that here the cation is lead, and lead is one of the exceptions. So because it's that particular exception, that is going to form a precipitate. So this one is also not soluble in water. Okay, let's look at Hg2Cl2, mercury chloride. 15 said, 50% of the class said soluble, 50% said insoluble. Whoa, 50-50. So here, chlorides, if they're in a compound, are soluble unless Hg2, 2+, is the cation. All right, and here, Hg2, 2+, and how do I know it's the 2+? Because I have 2 chloride anions. All right. So we have Hg2, 2+ is the cation, and we have Cl-, and I have 2 of them, all right, in my compound. So because Hg2, 2+ is the cation, this one is going to form a precipitate because it's an exception. Usually chloride is soluble if it's the anion. Those compounds are soluble, but because our cation is Hg2, 2+, it will not be soluble in water. It'll be a precipitate. Okay, and if people have questions on this as we go, 50% of the class said it would be soluble. So don't hesitate to ask me or tell me you're confused if this is not clear. Number 4, sodium sulfide. So let's look at our list. I see sodium up here. Okay, anything that contains sodium is going to be soluble. Are there any exceptions? No, none. So sodium sulfide will be soluble. Yes, and 80% of the class got that one correct. Number 5, ammonium phosphate, NH4. We have 3 of them, PO4. Let's look at our list. I see ammonium, very first cation. Any compound where ammonium is the cation is soluble, no exceptions. Okay, so yes, this one will be soluble in water as well. And 70% of the class got that one right. Questions? Okay, you will have access to this table for the exam. but make sure you, just because you have it, okay, doesn't mean you know how to read it. So make sure you understand the things we just talked about and the exceptions in particular. Okay. All right. So I'm going to move on with one more practice to kind of check your comprehension here. I have a chemical reaction on this screen, and I want you to write the products. And I want to know, are they going to be soluble or insoluble? So look at your reactants here. We have silver nitrate, AgNO3, and we have sodium carbonate, Na2CO3. They are two ionic compounds, but they're both aqueous, meaning they're both soluble in solution. And how do we know what products we're going to get first off? How do we even know what to write? It all goes back to one of the videos from last Thursday when we talked about the single displacement, double displacement. What we have here is two ionic compounds. This was like the example where I wrote the AB plus the CD. When you have two ionic compounds, this is set up perfectly for double displacement. So what we have here is a double displacement reaction. And what happens in a double displacement reaction? Anybody remember? I see some of this. Yeah, the cations and the anions switch. Okay, so we're going to take A and we're going to pair it up with D. And let me switch colors here. We're going to take B and we're going to pair it up with C. And we're going to write our new compounds this way. Remember to always write the cations first. So what are we going to form? It doesn't matter which compound I write first as long as I write my cation first and my anion second. So I'm going to take silver as my cation from my first compound, and I'm going to pair it up with the anion from my second compound. So I should have, and we have to write the formula correct. Don't worry about balancing just yet. So Ag, well, what is the charge on silver? How do I know? I should be able to look at my compound and determine that. Nitrate, NO3, if I'm looking at this first reactant here, NO3 has a -1 charge. How many nitrates do I have? I only have one nitrate anion. So that's a total magnitude of -1. Well, how many silver cations do I have in this compound? I don't see a subscript here, so that means there's just one. So that means it is a +1 to balance to form a neutral compound. So silver is a +1. Carbonate is a polyatomic. You should know its charge. It's a -2. So I have Ag +1 and I have CO3, whoops, -2. So how many do I need in my compound? Do the switch trick. I need 2 silvers and I need 1 carbonate. So it's going to be Ag2, CO3. Okay, so that's one compound. Now, is it soluble or not? Let's look at our solubility rules. I'm going to erase a little bit because when I write all this, it looks cluttered and I can't keep things straight. I don't see silver on here anywhere. It's not any of my cations, and I don't see carbonate. So is silver carbonate soluble or insoluble? It is insoluble, meaning I'm going to put an S right here to indicate that it will form a precipitate. Okay, but what's my other compound? Let me get my pink. I'm going to take the cation from this, my second compound. I'm going to pair it up with the anion from my first compound. So I'm going to have sodium nitrate. And how many sodiums, how many nitrates do I need? Well, sodium is a main group 1, so it's going to form a cation with a +1 charge. And nitrate is a polyatomic. We already wrote the charge for it. It's a -1, so I just need 1 each. I need to write smaller over here. NaNO3, okay, because this is a +1, this is a -1, so I get a neutral compound when I have 1 each. Now, is sodium nitrate soluble or insoluble? Let's look at our solubility rules. I see sodium right here. If sodium is your cation, no exceptions. And look right here, if nitrate's your anion, it's soluble, no exceptions. So this is definitely, I don't have room to write it on the same line, but I'll write AQ. Okay, I'll write AQ to indicate it is not going to form precipitate, it's soluble. So questions there. Oh, why hasn't anybody told me to shut the poll? I don't know if that's still on your screen or not. Okay, y'all feel good with precipitate reactions. How do you tell if you get a precipitate reaction? If you see a little abbreviation with an S indicating something's a solid on one of your products, or if you use the solubility rules, you should be able to write those in. Okay, we're going to move on to the second kind of chemical reaction that we're talking about today. I know we talked about 5 last week, so total we'll have 8 classifications. And this one is an acid base.
Miss Everly?
Yes?
We have a question in the chat.
Why was silver a +1 charge and not 2? Great question. Let's go back and look at that. Well, let me erase. Oftentimes, if you're unsure how to figure out for different cations what the charge is, well, if it's a main group cation, like main group 1, 2, or 3, you should always know what kind of charge it will have. If it's a main group 1, it'll form a +1 charge, like sodium, lithium. If it's a main group 2 cation, like calcium or barium, it'll form a +2 charge. If it's a main group 3, like aluminum, it'll form a +3 charge. Okay, so there the main group numbering matches the charge it forms as a cation. But if it's a transition metal, like silver here, then sometimes you can have metals that form multiple charges. Silver happens to be a transition metal that only ever forms a +1, but you didn't have to memorize that. There's actually a way to know that just by looking at the compound. You look at the anion. Okay, you look at the charge on your anion, and then you consider how many anions do I have, and you calculate the total magnitude of negative charge. So our total amount of negative charge from our anions was what? Well, we have 1 NO3, and it has a -1 charge. How do I know? That's one thing I asked you guys to memorize, was your polyatomic odds. That's one of the polyatomics I asked you to memorize. So if you need to go back and work on that, this is something you should know. So a nitrate has a minus, and you still have your chart of polyatomic ions, okay? So you can always look at a chart. So I have 1 nitrate and I have -1. So the total amount of negative charge here is -1. Well, I know that my compound is charge neutral. It's got to be. We don't write compounds that are ionic compounds that are not charge neutral. Okay, we write ions that have charges, but if something is written as a compound, it's because overall it's neutral. So that means the total, total amount of positive charge also is +1, okay? Because we know +1 and -1 add up to 0, and that means that I have a charge neutral compound. So I know my total amount of positive charge is +1. Now, I know I have silver. How many silver cations do I have in my compound? Oh, Caitlin, you asked a question in the chat. I'll answer that in just a second. Sorry, everyone, I was reading that question. The total amount of positive charge is +1, and I have 1 cation. So that means the charge, if I just have 1 of these, I looked at my subscript up here, I don't have anything, so that means I have 1 silver. That means that silver carries that total amount of positive charge, okay? So that's kind of how you walk through figuring that out for transition metals. It's the hardest for transition metals. Like if it was copper or iron or nickel or something like that, you need to look at your anion, consider the charge on that anion. How many anions do you have? What's the total amount of negative charge? Then how many cations do I have? And that means how much should each cation carry, okay? We figure it out that way. The question in the chat, AgNO3 has a coefficient of 2. Does that carry over the product side? Yeah, I actually didn't balance it, did I? So the question doesn't say to balance, but for good habit, we should always balance. I actually have a coefficient of 2 here because I believe, yeah, when I wrote my compound, Kate, look, I had to write in 2 silver cations, all right, to write the formula correctly. So I have 2 silvers on both sides. okay? I have 2 nitrates. I need to have a 2 right here. So to fully balance this equation, I should have added a coefficient of 2. Now I'm balanced, and I have the same number and kind of atoms on each side. Any other questions? All great questions. Thank you guys for stopping me. All right, acid-base neutralization. So this is the second kind. We said we got precipitation. Now let's talk about acid-base. This commonly occurs between an acid. We abbreviate acids like this, HA, okay? The A here stands for the word acid. And we will learn in chapter 10 that acids, they donate H+. They have what we call an acidic hydrogen, and they give those away. Okay, that's what makes it an acid. Okay, the fact that HCl is very corrosive is because it gives away hydrogen ions like crazy. So we always write the little hydrogen ion in to indicate that we have an acid. And a metal hydroxide. Okay, what is hydroxide? It's OH minus. So I'm going to abbreviate this as MOH. M stands for the metal. It could be a transition metal. It could be a main group 1 or 2 metal. So the acid-base reactions commonly occur between an acid and a metal hydroxide, okay? If the acid is HA, the acid, then the metal hydroxide is the base, right? Because this is an acid-base reaction. So this right here, the metal hydroxide is your base. And what do they make? They yield water and a salt, okay? Now, the fact that we're making water here, we know water has a pH of what? Anybody? We actually haven't talked about pH, but this is somewhat common knowledge. pH of 7, neutral pH. So why do we call it acid-base neutralization? Because you're forming a neutral compound. The acid and the base are, they have opposite effects on one another because of the things that combine, and you make water. So a key sign, write this down, a key sign that an acid-base reaction is what you have on your hands is that you're going to make water. One of your products will be liquid water. Now we're actually going to expand this definition when we get to chapter 10. So this is a limited definition. I'm not telling you a lie, but it's just we'll expand it when we get to chapter 10 to have a deeper understanding of acid-base. But for now, you can know. How do I know if I have acid-base? Well, look at your products. If one of them is liquid water, that's an acid-base reaction, okay? All right, now tip. The H+ ion, here's what's happening. The H+ ion from the acid combines with the hydroxide ion, OH minus, from the base, and that's where we get water from, okay? So we have 2 ionic compounds. You take the hydrogen cation and you combine it with the hydroxide anion. You make water. And then the anion, okay, so what's left over from the acid, which is what we're calling the A minus, all right? If we have, let's zoom in really quick right here. If we have HA, H+ is our cation, and that means the acid, A minus. Whatever's left over, that's your anion. So we're taking the anion from the acid. It could be any kind of anion. It could be chloride, it could be iodide, it could be bromide, it could be sulfide. Combines with the metal or the cation, CATION, from the base, and that's what gives us our salt. So let's look at an example right here. Now, I will tell you, acids kind of break a few rules when you come to writing ionic compounds. I want to look at this thing right here, CH3COO. That part's in red, and then you have an H in black. This is an ionic compound. This is acetic acid, but we have CH3COO minus, and then we have H+. Normally we write the cation first, right? And I know you're thinking, why is H last? Well, again, sometimes acids break a few rules here. When you write acetic acid, that H is written last. But normally we write the cation first. Okay, so this is the ionic compound. This is our acid. And what's in black, that hydrogen, that is our acidic hydrogen. All right, and then we have our base. This is the metal, sodium, okay? This is the metal, M, and then OH minus is our hydroxide ion, and it's in black. So we're gonna pair up the things that are in red, and we're gonna pair up the things that are in black. And when we pair up the things that are in red, we will write the cation first. So let's do that. Let's get, we know H and OH, that's gonna make water, H2O, and it's a liquid. So we paired up the things that are in black. I guess I could write it in black to help us out. Let's go to red. Now we're going to pair up the things in red. So I have a sodium cation. And then what is CH3COO? That's acetate. That's an anion from our polyatomic list. And people write it different ways. Sometimes you see acetate written as C2H3O2. Sometimes you see it written here, CH3COO. Sometimes you see it written as CH3CO2. But it's all the same thing, okay? These are synonymous with what I boxed in. All the same number of elements there. But just, I know it's confusing. It can be written different ways. And I should not have written the charge here. So we have sodium, and then we have CH3COO. And that is also aqueous. Because anything with sodium and anything with acetate, those are soluble, no exceptions. Questions on what we just did? Let's do a practice problem to see how well we comprehend acid-base. So I want you to write and balance this equation that I have typed out. I want you to write the formulas. Cesium hydroxide and hydrogen sulfate react to yield what? And I want you to try to label which one's your acid and which one's your base. Cesium hydroxide. If you need a periodic table, grab one. Cesium is CS. Sulfate, you should know, is SO4, 2 minus. So you need to be brushed up on your rules for writing ionic compounds. Remember, I said chemistry is something that builds on itself. So if you were no bueno with chapter 3, chapter 5 is going to be exceptionally hard. All right, I'm going to start writing it. Hydroxide is OH minus, and then hydrogen is H plus. So for cesium hydroxide, we should have, cesium, I believe, is a main group 2. So you should have CS, and then how many hydroxides will I need to balance that to make a neutral compound? Do the switch trick. Because it's a polyatomic, I'm going to write it in parentheses because I need 2 of them. Hydrogen sulfate. How many cations, how many anions do I need? Do the switch trick. I'm going to need 2. I only need 1 sulfate. Oh, CS is in main group 1? Sorry, everyone. Clearly, I have the periodic table just all kinds of memorized. Then we should just have that. There we go. But over here, we should have SO4. Okay, so those are your reactants. Now, remember, we're going to take OH, and we're going to take hydrogen, and we're going to make water, H2O. Don't worry, we'll come back and balance. And then we're going to take the metal to make the salt. Metal and what's left over from the acid. So it's like a double displacement reaction. So we should get, or I'll just write it like this. CS, how many cesiums do we need? We said this is a +1 and sulfate is a -2. So I'm going to need 2 of these. So CS2, SO4. Okay, is that soluble? It is. If you look at the solubility rules, it's aqueous, and then water obviously is our liquid. Now, are we balanced? Well, no, we're not. We have 2 cesiums on the product side, so I need to come back and put a 2 right here. Are we balanced then? No, because we have 2 oxygens and we have 4 hydrogens. So if I put a 2 in front of water, now I think we're balanced. Any questions on that? So how do you know if you have an acid-base neutralization reaction? You form water. Okay. How do you know if you have a precipitation reaction? You form a solid or precipitate. All right, so that's 2 of the 3. Let's get to the third one. I'm going to introduce the third one with this slide. So you see a bunch of different pictures here. I want you to look at these pictures and try to ask yourself, what is represented in these pictures? These are medical devices. So you guys are all future health professionals. That doesn't mean you have to be going to nursing school to care about this kind of stuff. These things affect a lot of different lives. Some of you may have family members who have this kind of stuff. But what do these things have in common? Well, this first picture in the top left, anybody know what this is?
Pacemaker.
It's a pacemaker. So my grandfather back in 2016 went on like a year-long bout. He was in and out of the hospital for a while with congestive heart failure. He's in his 80s, so it's kind of risky for them to perform surgery. So a lot of you may have older relatives who their hearts are wearing out. And there's lots of different medications they can take, but sometimes if you're young enough, surgery is not risky and you can get a mechanical heart or a pacemaker to help keep your heart in rhythm. So that's very beneficial. It's this little battery-operated device that just keeps your heart pumping the way it should. Okay, what is this picture over here? Anybody know what we call that? It's called a cochlear implant. Okay, kind of a technical name, but people who are deaf, you can actually get cochlear implants, or people who experience a lot of vertigo, you can get these to help maintain an equilibrium or to help your brain pick up auditory stimulation. All right, so it helps deaf people hear different stimulations, and it doesn't make them, hear perfectly, but it can help. All right. Again, it's a small battery operated device that just helps in that regard. And then on the bottom here, a lot of people who go off to war and experience things like PTSD, or you don't have to be a veteran. There are just people who have post-traumatic stress disorder. You can't, but a lot of veterans have it. And so you may know somebody, you may have somebody in your family that experiences this kind of stuff. And it's very serious, okay? It can alter life in huge ways. And so what can happen is they can get brain implants, and this is not an easy decision, right? This would be a huge decision, but to help regulate different nerve impulses that can alter your attitude and your mood. Now, some people obviously would not want to just feel like they're a robot and would rather deal with it, and a lot of people do. Again, it's a small battery operated device. So the question, what do all these things have in common? They're all run by small batteries, okay? And batteries aren't just important in the health profession realm. Batteries impact our life all day, every day. How many of you are like, my phone runs out of battery every day by noon? Okay, that's me too. We depend on our chargers. We depend on recharging batteries so that we can operate, communicate. A lot of research and technology are built on batteries. And so that is the foundation, or that's one helpful application of the next kind of reaction we're going to talk about, which are redox reactions, okay? Batteries are run by redox reactions, all right? And batteries are important in all realms. So, and that's not the only thing redox reactions are useful for, but it's a main one. So we call these oxidation reduction reactions, or we abbreviate them redox. Oxidation reduction, also known as redox reactions. Okay, so what is this? A redox reaction is one in which electrons are transferred from one atom to another. Okay, so this sounds just like an ionic bond, right? We're just transferring electrons. So there's some similarities here. I think at a conceptual level, you can understand the foundation of what's happening in a redox reaction because you're familiar with electrons being transferred from one atom to another. But we're going to have some slight nuances with the fact that we're not going to address these things from a charge standpoint necessarily, like what charge does it carry. We're going to call them oxidation numbers, and I'll get into that in a minute. So oxidation is the loss of one or more electrons, and reduction is the gain of one or more electrons, okay? Now, the way people keep this straight in their head, because it can be confusing. When you are gaining electrons, people tend to think, oh, I'm gaining charge. I'm increasing in charge. But you're not. When you're gaining electrons, your charge is being reduced because you're gaining something that has a negative charge, right? So your charge is becoming increasingly negative. That is reduction. So oil rig is an abbreviation that helps with that. It says oxidation is the loss and then of electrons, okay? And reduction is the gain, okay? R-I-G-O-I-L, oil rig. Okay, so that's just a little helpful tip there to keep oxidation and reduction straight in your head as far as what's happening. This figure is in your textbook. It just shows you an example of oxidation and reduction. So if you follow any one of these lines, 1, 2, 3, or 4 here, from the left to the right, then you are seeing something as oxidation. That's oxidation. Anytime you go, let's look at the first one. If we have something with a -2 charge, okay, and it then makes something with a -1 charge and it gives away an electron, we have lost an electron. That is oxidation. So the point that I want to make with this figure is you don't just have to be going from a 0 charge to a +1 charge to be called oxidation. It's any kind of change in charge that's becoming increasingly positive because you are losing electrons. You're giving away electrons, so your charge is changing towards the positive direction, but that doesn't mean you are ending up with a positive charge. So the example from going from a -2 charge to a -1 charge, that is oxidation. You still have an anion. Okay, you don't have to be a cation to be oxidized. Does that make sense? That's where redox gets confusing with people because you're so used to categorizing things as cations and anions as you understand the trade of electrons. But you can trade electrons and still be an anion, okay? Or you can be oxidized and still be an anion. All right, now if you follow this, let's look at the blue arrow down here. If you follow this figure from the right to the left, what you have is an electron plus something, so something's gaining an electron and the charge is being reduced, okay? All of these things over here on the left side of the figure have a lower charge than their counterpart, the reactant on the right side of the figure, okay? So if you gain an electron, your charge is becoming increasingly negative. That doesn't mean you're an anion, it just means your charge is reduced, okay? That's why we call it reduction. Okay, questions? Did I explain that? Confusing enough? Confusing enough? We're gonna look at some examples. This is the hardest kind of reaction to get straight in your head. It's the hardest to identify. It's the hardest period. So we're ending with the most challenging one. Okay, here's an example. We have copper and then we have silver nitrate. And what we're making is silver and copper nitrate. So what kind of reaction is this? Combustion, decomposition, combination, single or double displacement. Does anybody recognize? Look at what's happening. We have something by itself, and then we have an ionic compound, silver nitrate. And if you look at the product side, the copper and the silver switch places essentially. So what we have here is we have a single displacement reaction. Okay. All right, so here's the questions. What's happening to the copper? What's happening to the silver? Well, look at these test tubes. This is what's happening. You have copper, all right, we have this copper wire. You can kind of see it's a copper color. And this solution right here, this is your silver nitrate. It's a clear solution. And how do we know? Well, it's aqueous. But when they react long enough, what you see happening is this copper wire begins to dissolve and you see all this kind of weird, it's silver but it doesn't look like clean polished silver. So we're forming silver, and then we're forming, you see how the solution turns a blue color, kind of a bluish green color? Anybody ever worn copper jewelry before? My husband, his very first wedding band was he wanted copper, okay? I just let him get it because he wanted it. But his finger would always turn green, like when he would wash his hands and stuff, it would turn like a bluish green. That's because that's what copper does when it's wet. So in solution, copper turns kind of a bluish color. So this is the copper nitrate. Okay, that solution. So things are switching places. That's just a picture of what's happening. But let's look at the equation down below. So copper, I'm looking right down here. On the reactant side, what you have to do to determine what's being oxidized and what's being reduced, and if you have a redox reaction, is you have to see, is anything changing charge? Is anything changing charge? Is anything increasing in charge? Is anything decreasing in charge? So that's what we're going to look at. Copper here is a solid on the reactant side. And what that means, anything by itself in its elemental form, it has a charge of 0. Here, copper is in its natural state. So on the periodic table, as written, it has a charge of 0. And on the product side, we see that copper is over here in the ionic compound. That means it's now a cation. So copper went from 0 charge, and if you follow this red line over, okay, now it has a +2 charge. So copper went from having 0 to +2. So did it gain or did it lose electrons?
It gained. Lost.
There's debate. Someone said it gained, someone said it lost. What do y'all think? Any other comments? Okay, people are saying in the chat that it lost, and that's correct. It lost 2 electrons. Remember, when you give away things with negative charge, your charge becomes more positive. So copper lost 2 electrons. And so was copper oxidized or reduced? Let's go back up to our definitions. Remember, oxidation is the loss of electrons. So copper here is being, see, when we ask this question, what happens to copper? It is oxidized. Okay, now let's answer the second question. What happens to silver? Well, silver is right here initially. On the reactant side, it's a cation. Okay, silver only ever carries a +1 charge. You don't have to have that memorized. You could figure that out from looking at your compound. But that's what we've written here, is we've written that it has a +1 charge. On the product side, silver is right here, is by itself. And anything by itself in its elemental state, in its natural pure form, it's going to have a charge of 0. So over here, I'll do it in blue. It's got 0 charge. So it went from +1 to 0. Silver goes from +1 to 0, and copper went from 0 to +2. All right, sometimes it helps if you write those things out like this. So did silver gain or lose electrons? Brennan said it gains. Okay, so this gained, we'll say gains electrons. All right, now there's 2 silver cations, and on both sides we're balanced, and each one gains 1 electron. Okay, so we're still trading 2 electrons total in the reaction, but it's just that we have different numbers of ions. Okay, so each silver cation gains 1 electron. Total, 2 electrons are gained. So was silver oxidized or reduced? If its charge was from +1 to 0, its charge was reduced. So silver was reduced. Okay, I told you this is the most complicated thing we're going to talk about. But let's fill in the blank down here. Redox reactions involving ionic compounds are usually straightforward. You look at the change in charge to determine which one's reduced and which one's oxidized. Okay. Wow, we're running out of time. So we won't get to the review material that I wanted to get to today, but since we have a whole review day scheduled for exam 2, I'll try to make sure we get to it then. Let's look at another example though. I have an entirely different equation. I have potassium and I have bromide. Okay, and the questions here, what happens to potassium? What happens to iodide? So let's look at this. We have potassium iodide. That's our first reactant. It's an ionic compound. And then we have bromine. I say bromine. It's a diatomic. So that's why I rewrite it with a Br2. And then on the other side, we have iodine. It's also a diatomic. And then we have KBr. Again, this is a single displacement reaction. A lot of the times, I'm not going to say always, but a lot of the times a single displacement reaction is a good indicator that you have a redox reaction. A single displacement reaction, you might want to make a note of that. A single displacement reaction is most of the time a redox reaction because you have something with a 0 charge on one side and then something with a negative or a positive charge on the other side. So let's look at what's happening to iodide. All right, iodide on the reactant side, it's right here. It's in Ki. That means it's an anion. It's written second. So what's the charge on I? It's main group 7. We know those form anions with a -1 charge. So that's what we have right here. Iodine at first is a -1. And this 2 is just because we start out with 2 of them. Okay. Now, let's look at what happens on the product side. We have iodine right here. It's by itself. Anything in its elemental state by itself has 0 charge. It's neutral. So if we go from a -1 to 0, so iodine, that's our second question, goes from -1 to 0. That's the change in charge that is occurring. Did it gain or lose electrons? Did it gain or lose electrons? It loses electrons. Okay, when you give away something negative, your charge increases. Here we're going from -1 to 0, our charge increases, so it loses electrons. So does that mean it was oxidized or reduced? If we're losing electrons, what did we say? Are you oxidized or are you reduced?
Oxidized.
Oxidized. So what happens to iodine? It is oxidized. Okay, so bromine, let's look at bromine. Bromine starts out right here. It has 0 charge, it's by itself. And on the product side, it's the anion. We know anions carry negative charge. So if you look at this figure down below, that's what we see. It starts out with 0 charge by itself. On the product side, it's a -1. So did it gain or lose electrons? It gains electrons. Oh, I think this should not have been potassium. I think this should have been bromine. That's a typo. Because we aren't even talking about potassium down here. Potassium is the same charge on both sides. It's the cation on both sides. So sometimes you'll see things that don't change charge at all. And you're not interested in those things. You're trying to find the things that do change charge. So if bromine gained electrons, it went from, 0 to -1. Was it oxidized or reduced? Its charge is decreasing, so that means it was reduced. And that's kind of what's detailed down here in all of this text. It says an iodide, what's happening? Ion gives an electron to bromine. So iodine is losing, bromine is going to pick those up. So an iodine ion is blank. As its charge increases, we said oxidized. From -1 to 0. Bromine is reduced as its charge decreases from 0 to -1. Okay, so that's oxidation reduction. Now, really quick, I'm going to talk about these numbers that we're writing in, okay, like these things, these numbers. I know we're saying that's the charge, and you are essentially This is where redox gets kind of nuanced because what we're actually writing in here are the oxidation numbers. Okay, we call them oxidation numbers. What are they? These are values we assign to atoms to indicate whether an atom is neutral, electron rich, or electron poor. Okay, what is an oxidation number? It is a value. Notice I'm saying value and not charge, okay, because there will be times where an oxidation number will be different than an atom's typical charge. So it's a value, but it makes us think of charges. They're similar in a lot of cases to indicate whether an atom is neutral, electron rich, or electron poor. Now, here's what I'm going to say. We're running out of time. We have 2 minutes left. You need to go read pages 151 and 152 in your textbook. This is where your textbook talks about oxidation numbers, okay? So because we're not going to have time to really finish this, I'm going to fill in these slides on this, or fill in the blanks on this slide, and then we're going to be done. I want you to go read those pages, okay? So here's the rules. And by the way, right here, oxidation numbers do not always necessarily imply somebody's charge, an ionic charge, but they are similar in a lot of cases. So here's what you maybe have just learned from the past 2 things we did, those 2 reactions we just talked about. An atom in its elemental state, when it's by itself, will always have an oxidation number of 0, okay? What we saw, I'll come right back, but that's what we saw. Let me zoom in with like bromine, okay? Right here we said it's, now again, I know we're using the word charge, okay? We said when it's by itself, 0 charge. Same idea with iodine. On the product side, it was by itself, so we said it has 0 charge. That's actually the oxidation number we're writing in. Something by itself has an oxidation number of 0. Okay, then we're going to say a monatomic. What does that mean? Mono means 1, a single atom ion. So not a polyatomic, a single atom ion. A monatomic ion has an oxidation number equal to its charge. If it were an ion, what charge would it be? That's the oxidation number we're going to give it. Okay, so for example, iodine, bromine up here, up top, in this reaction, we said as an anion, it carries a -1 charge. So that's the oxidation number we're going to give it. As a monatomic ion, when it's by itself, has an oxidation number equal to its charge. In a compound, an atom usually has the same oxidation number it would have if it were a monatomic ion. Don't get confused by all this wording. This is stuff that you actually already pretty much inherently know if you understood ionic compounds and how to write them. When you just think, okay, what type of charge should my cation have? What type of charge should my anion have in this compound? The oxidation number is usually the same. That's all rule number 3 is saying. Now, rule number 4, the sum, so the sum total of all the oxidation numbers in a compound have to add up to 0. Again, we're keeping the same rules here that we have a neutral compound overall, okay? Example is with HNO3. This was actually a problem on the homework that I removed from chapter 4. Somebody brought it up. This is an ionic compound, okay? But if we assign oxidation numbers to this, remember we have H plus and we have NO3 minus. If I assign oxidation numbers here, nitrogen gets an oxidation number of +5. And each oxygen, there's 3 of them, gets a -2. Because total, everything has to add up to -1. Okay, so what's bizarre here is what I'm going to circle in red. Nitrogen having a +5 oxidation number, that's bizarre. Okay, I've officially gone over time, so I'm going to stop. What we got to is just practice problems. And so if you want to work these, you're just figuring out what's oxidized and what's reduced based on the rules we talked about. But I will try to pick up with some of this stuff. I don't know, I might post a video of walking through this stuff and solutions for you guys and put it on Blackboard, because I don't want to necessarily take up a ton of lecture time on Thursday since we got to get into chapter 6. So we did not necessarily finish what I wanted to get